Over the course of the semester, we've been spending a lot of time developing arguments for and evaluating arguments for a very broad kind of theory of human language understanding that puts together the following key theoretical ingredients. The first is Bayesian inference. The idea of Bayesian inference is that language understanding is well posed in a very broad sense as a problem of inference under uncertainty. We get inputs, and we're trying to analyze them to identify the structure of that input or the meaning of that the input is intended to convey, or both. And this is applicable down from the level of identifying which sound category was perceived at a particular part of a word, like D versus T in a word like dent, all the way up to the overall syntactic structure of a sentence, and even beyond to the sophisticated aspects of meaning that a speaker is intending to convey. Bayesian inference says that we take an input and we reconcile it with, on the one hand, the prior probability of possible structures or meanings that could be assigned to that input, together with a likelihood that the input would have under any particular structure. Those two things are reconciled via the principles of probability theory to form a posterior distribution over analysis of the input. The second ingredient is probabilistic grammar. The idea of probabilistic grammar is that we have not only knowledge of what possible structures for language are possible, but also expectations about when particular structures are likely or unlikely to be deployed. And those expectations can be conditioned on various features of the context. And so, for example, a simple probabilistic grammar is a context-free grammar that has probabilities on it. It scores trees as the trees have probabilities according to the product of the pieces of the tree that are required to assemble it. And the third idea is surprisal. The idea of surprisal is that what makes something difficult or easy in context in real-time processing is its log probability. So the negative log probability in particular, or the log of the inverse probability of something given this context, is going to determine its difficulty. And this theory overall, in tandem, you've seen it applied to unify many different kinds of problems. These include global disambiguation, like what structures are going to be more likely to be interpreted as a particular utterance holding. Garden pathing analysis, so for example, for sentences like when the dog removed the muzzle, the context sets up the one expectation. The continuation is consistent with a structure that is not the one that was expected before, but one that's disfavored. That makes things hard. And prediction and reading time. So for example, the word play is very probable in the children went outside to as a context, much less probable in my brother came inside to as a context. We know that affects real-time processing behavior, and we even know that there's a systematic quantitative relationship between the probability of a word in its context and, for example, how long it takes to read. In particular, the log probability of a word has a linear effect on reading time. I also want to remind you that over the past several weeks, we've seen how deep learning models that are trained on large unannotated data sets turn out to have emerging from them, if they're left-to-right models, we can test them for their surprisal behavior on controlled experimental sentences like we would use in psycholinguistics experiments. And it turns out that you get remarkably syntax-like surprisal behavior from these deep learning models. And this ranged from garden pathing, examples like we see in the lower left, to filler gap dependency processing like you see in the lower right. So with all of this in account, in context, I want to actually pose what turns out to be a puzzle for incremental inference accounts that are based on surprisal. And the example sentence is the following. The coach smiled at the player, tossed the frisbee. Now, if you haven't seen this sentence before, you probably find it hard to understand. And I want to, first of all, convince you that it's real sentence of English. And second of all, give you an understanding of why it would be so interesting that this is a hard sentence to understand, and give you a bit of insight into maybe why it's hard to understand. And actually, we'll be developing a theory of why this sentence is hard to understand as a sort of during the rest of today. So first of all, take the sentence, the coach smiled at the player, tossed the frisbee, and compare it with the following minimally differing versions. First of all, let's take the coach smiled at the player, thrown the frisbee. For many of you, this may already immediately be easier, but for some people, this is still a sort of strange sentence. I think for everybody, people are going to find this sentence perfectly fine. The coach smiled at the player who was thrown the frisbee. Now, I want you to remember a couple of things about, we've studied before, relative clauses and about part of speech ambiguity. First of all, relative clauses that have the word sequence who was or who is can have those words dropped. Those are passive voice relative clauses that can be reduced. And the process of eliminating the words who was or who is or who are is the process of reduction. So going from this who was version in C to the who was to the no who was version in B is a general rule of English. We've seen this in other cases before. So if C is okay for you, then even though B might be a little more weird for you, you'll probably recognize that it's fine. Another thing to notice is that thrown and tossed are actually synonyms in the right syntactic context. So I can take C and I can replace thrown with tossed, and I get the coach smiled at the player who was tossed to the frisbee. And if you found C okay, you probably find D okay as well. Now notice that by analogy of converting C to B by reducing the relative clause, I can also convert D to A by likewise reducing the relative clause. And so if D is acceptable, which I think it probably at this point everybody agrees that is a perfectly fine sentence of English, the coach smiled at the player who was tossed the frisbee, then A should be okay for you too. The coach smiled at the player tossed the frisbee. Nevertheless, you probably still find that A is weird. You may understand what it's supposed to mean now, but this is a very weird and difficult to understand sentence for almost all native English speakers. Now, this has been studied using incremental processing techniques, and it turns out it's very reliable effect that readers boggle at the word tossed in version A in a way that they don't boggle at tossed or thrown in versions B through D. So this was first demonstrated by Tabor et al. 2004, and here's the original, around this word tossed, here's the original self-paced reading graph. So word 0 in this graph is the word tossed or thrown. And you can already see a pattern distinguishing the four conditions emerge, but really it turns out that in self-paced reading, at least for this sentence, the boggle phenomenon really emerges and is maximal one word after. It spills over to one word downstream of the target word. And so this point right here, which is the processing time of the word this spike is really the clearest place where you can see the difficulty boggle. And you'll notice that the pattern across the four conditions is what's called superadditive. That is that, so in this example, the solid versus the hollow points is reduced versus unreduced sentences, and the triangles versus the squares is part of speech ambiguous words tossed versus part of speech unambiguous words thrown. And what you can see is that this is a superadditive difficulty pattern. That is that the effect of reduction, for example, going from the square, the hollow square to the solid square, is smaller for part of speech unambiguous words like thrown than it is for part of speech ambiguous words like tossed. So this effect, this jump is, the second jump is larger than this first jump. Okay. So that's the empirical behavioral signature. And of course, it probably didn't require reading times. It sort of manifests to most people that A is harder by far than B, any of B through D. Now, why is this theoretically interesting? We've seen a lot of cases of what seem to be processing difficulty from various sorts and their incremental effects and their measurable reading times. Why is this one particularly interesting? So remember that this probably bears a family resemblance to what we've seen in classic garden path sentences. And in some classic garden path sentences, part of speech ambiguity leads to misinterpretation further on. So we're very early on in the semester, we looked at the sentence, the women brought the sandwich from the kitchen tripped. Now, theoretically, we understand the difficulty of the word tripped in this context by recognizing first, well, look, the word brought is interesting because the word brought could be a simple past tense verb, but it could also be a participial verb. However, in this context, at the beginning of the sentence, by the time you get to brought, it's a very appealing interpretation to say that brought is a simple past tense verb. Simple past tense structures are the most common kind of structures in this part of the sentence. The woman is a perfectly good subject for the word brought. There's a very simple syntactic structure, which I've illustrated on the right, which exemplifies it. And so this is a very appealing interpretation to take of this sentence in this context. However, the difficulty comes when the word tripped is not integratable with this structure. There's no way of, before the word tripped, there was nothing in this sentence that creates difficulty, but tripped is not accommodatable. Instead, there should be a very different kind of syntactic analysis, and tripped would fit in as the main verb in that. So the coach example that we just saw is similar to this, but there's actually a crucial difference, which is the context, quote unquote, should rule out the garden path. So let's look at this sentence. The coach smiled at the player tossed. As with the word brought, tossed is part of speech ambiguous between a simple past tense verb and a participial form. I was tossed the frisbee, I tossed the frisbee, same form. And so you might say, well, maybe this is just an ordinary garden path effect. But what's different about this setting than with the woman brought the sandwich setting is that now the broader context in which the word tossed occurs is one that already rules out a simple past tense verb. So there's no way of integrating this kind of structure into where we are, which is a prepositional phrase. And therefore, this part of the analysis that seems to be what might be causing the difficulty, or if we were going to try to make an analogy with the sentence up here, then it would be a non-starter, because we already have all of this evidence that the context is taken into account very rapidly, very thoroughly, and ubiquitously in human language processing. So according to our typical theories, it should be the case that that tossed is interpretable in exactly the same way as we would be able to interpret a part of speech unambiguous verb, in this case, like thrown. The context rules out the simple past tense verb, therefore we only interpret it according to this participial form. That is, that this apparently appealing analysis should just not be possible. But it seems to be, I think you probably had the interpretation that, you know, the tossed is a simple past tense verb, and something before it is the subject of that verb. And that is a challenge for the kinds of rational models built through the process of rational analysis that we've developed in this semester so far. This seems to be a failure to condition on relevant context. In particular, this extremely strong piece of context that we're inside a prepositional phrase, and there's no way that we could accommodate the beginning of a new clause at this point. So how do we deal with this? This is going to motivate a new kind of theoretical development that we haven't touched on really at the level of syntax in this experiment, in this semester so far, and it is the idea of uncertain input and language understanding. So the previous state-of-the-art models for explicit representation of ambiguity resolution was some kind of probabilistic incremental parsing. We've actually argued that even for deep learning models, there's some kind of implicit probabilistic incremental analysis that sort of follows some kind of structure. And we've also looked at probabilistic parsing models with grammars, and that has explicit ambiguity resolution. Now, throughout all of this, we've actually had a very important simplifying assumption, that the input is clean and perfectly formed. That is, that the input to sentence level comprehension is a sequence of word tokens. And that is something that we've sort of thought about at the level of speech recognition, how there can be some ambiguity in the phonetic input, for example. And we can manage that ambiguity using language understanding, using probabilistic models. But we haven't represented that on any kind of uncertainty about the actual input sentence, the input word sequence to date. Now, like all good simplifying assumptions, this one seems intuitively to be patently wrong. We know that we don't always perfectly treat the input that we get at the sentence level as a correct sequence, a sort of a vertical sequence of input tokens. For example, sometimes we misread what we've got in front of us. And also, I want to draw your attention to something which is actually a very sophisticated activity, which is proofreading. You've all done proofreading at various times. And proofreading is an amazing thing when you think about it. When you're proofreading, what you're doing is you're reading something, and then successfully proofreading can involve deciding that something you're reading doesn't actually mean what it literally looks like it should mean. Rather, it means something else, which is incompatible with what it actually says. And then afterwards, you figure out what you should have written, or what should have been written, for the sentence to actually mean what it should have meant, what it was intended to mean. This is a very counterfactual, hypothetical kind of reasoning. And this set of insights raises a number of following very interesting questions. So what might a model of sentence comprehension under uncertain input look like? That is, where the input tokens are not, it's not a vertical sequence of tokens, but it's actually an uncertain input. And what interesting consequences might such a model have? And so in the remainder of today, we're going to develop a model of sentence understanding under uncertain input and explore the consequences that we'll have for this particular example and for others.